Hello everybody, this is Dr. Bricker here with some hints for homework number 3. So homework 3 deals with chapter 4. Chapter 4 is all about Newton's laws of motion. So there's 3 laws. The second law is the only one that actually has a formula, and we'll see how this works out as we go through the homework assignment. Let's start with this one though. The figure shows 2 forces acting on an object as shown in the picture. So there's force 1 and force 2. We're just representing the object by a dot here. And we want to add a third force that will cause the object to remain at rest, and then let this new force be F3. Okay, so pretend this is a tug of war. You've got somebody pulling this way, somebody pulling that way. You want the dot to not move. Where do you have to put the third force? So we've got to balance force 1 and force 2. Force 1 has a part in the x direction and a part in the y direction. Force 2 has a part in the x direction and a part in the negative y direction. So how are we going to be able to draw this vector? Well, first thing, you can move these around. So I'm going to take F2 and actually put it here. So I'm putting the tail of F2 on the head of F1. And then I can add my third vector. Let's see here. Add F3. And okay, so F3 is actually, looks like down here. You can take it, move it around. I'm going to put the tail of F3 on the head of F2. And then I move this part over here. And if you notice up here, you could adjust the angle and things like that. So really what I've done is, this is F1 plus F2. What I have here is the opposite of F1 plus F2. It's pointing in the opposite direction. So then I can take this and put it here. That's what F3 would have to be to balance this whole thing out. And then you have to take F2 and put it back to where it began. Good, so really what I did was do F1 plus F2, but then the opposite direction to give me F3. And you can kind of fine-tune things with, select the vector, change the length, change the angle, that sort of thing. You want the angle to be 0 degrees. And let's see if this works. Submit. And good, correct. All right, so this F3 balances F1 and F2. I found this to be the easiest way to do this. This is kind of a fun problem because you get to actually move things around, digitally anyway. Let's look at the next problem. A skier is sliding down a 15-degree slope. Friction is not negligible. Identify the forces acting on the skier. So these are the forces just acting on the skier. I can't give you too much information, but the skier is not pushing themselves down the incline. We're just assuming that gravity is doing the work here. Friction is not negligible. So sliding down the incline, that means we have kinetic friction, not static friction. Okay, so I don't want to give too much information away. Review this section here. Okay. Let's look at the next one. A constant force is applied to object A, causing it to accelerate at 6 meters per second squared. The same force is applied to object B, and the acceleration is half as much. Applied to object C causes an acceleration of 9. What object has the largest mass? Okay, so remember, F is equal to ma. Okay, so constant force applied to A, same force. So the force is not changing. We're looking what happens to the mass and the acceleration. So if the force is staying the same, larger masses have smaller accelerations. Smaller masses have larger accelerations. Okay, I don't want to say too much to give this one away, but that's the idea here. Okay, so take a look at that. Just remember F is equal to ma, and the F part is constant in this problem. Okay, good. Next one. A man pulling an empty wagon causes it to accelerate at 1.4 meters per second squared. So 1.4 meters per second every second. So really that's what we did in the first 3 chapters. We looked at acceleration. We didn't know what was causing the acceleration at the time. When we get to Newton's laws, now we do know it's having a net force will cause an acceleration. Not just having any force, a net force. You could have several forces on an object and it's not moving, like we did with the first question. having a net force causes an acceleration. Okay, let's take a look at this one. Okay, so for this one, we don't actually know the mass of the cart. We just know for a given mass m, the acceleration is 1.4 meters per second squared. We want to know what is this new acceleration if you put 3 times that mass into the cart. So this new mass is the mass of the cart plus 3 times the original mass. So really this is 4 times the original mass, right? Because you've got the cart plus 3 times the mass of the cart in the cart. Okay, so the mass has gone from m to 4m. The mass has gone up by a factor of 4. What has to happen to the acceleration for that to happen? Okay, remember, F is equal to ma. So if you've made the mass 4 times as big, what do you do to the acceleration? Okay, let's look at the next one. Okay, so here we have a graph of acceleration on the vertical axis and force here on the horizontal axis. What is the object's mass? So remember, F is equal to ma. Here the force and the acceleration are changing, but the mass is constant. So F is equal to ma. You can pick any point you want here, really a nice convenient one to read. So let me just pick this one. For when the force is 1 Newton, the acceleration is 4 meters per second squared. So you can solve for the mass. So the mass is the force divided by the acceleration. Okay, so we've got 1 Newton divided by 4 meters per second squared. And then they want the answer in kilograms. So the answer comes out in kilograms. Okay, good. Let's look at the next one. In T-ball, young players use a bat to hit a stationary ball off of a tee. The 140 gram, okay, perfectly good unit, just not an SI unit. Divide by 1,000 to put this into kilograms. So it has the same, the ball has about the same mass as a baseball, but it's larger and softer. In one hit, the ball leaves the bat at 12 meters per second after being in contact with the bat for 2 milliseconds. If you read this quickly, it looks like meters per second, but this is the amount of time, 2 milliseconds. So 2 times 10 to the minus third seconds. Assume constant acceleration. First of all, what is the acceleration of the ball? Okay, we can get that from kinematics, actually. So we assume that the ball starts from rest, gets up to 12 meters per second. This takes 2 milliseconds. So we can figure out the acceleration. And then if we want to know what is the net force on the ball, well, now you have the acceleration and the force. You can figure out the net, you have the acceleration and the mass. You can figure out the net force. Let's take a look at this, though. So again, we're assuming that starting from rest, it's T-ball, it's just on a stand. The ball starting from rest gets up to 12 meters per second. This takes 2 milliseconds. How much is the acceleration? Okay, so here's the kinematics equation I have in mind. So starting from rest, the acceleration, this term is 0. The acceleration is final speed divided by the time. That's what it turns out to be for this problem. Okay, so let's see, we've got 12 meters per second, so 12 divided by 2 milliseconds. So here's how you enter that in your calculator, 2. And on my calculator, I've got this EE key. That means times 10 to the. So instead of writing times 10 and raise 10 to a power, things get messed up that way. You could just do this EE button. That means times 10 to the, and then minus third. And I'm using this this key here, this minus key, not the subtraction key. Okay, so minus key. 6,000. And you can see this is meters per second, so meters per second squared. That's the acceleration. And then to get the net force, it's m times a. The mass is given in the problem. Make sure you put it into kilograms. We just figured out the acceleration. Okay, good. So really a combination of what we did before in the previous chapters and then the new idea that we have, Newton's second law. Okay, let's go on to the next one. Okay, so your car is accelerating to the right. Okay, so if it's accelerating to the right, that means there's a net force to the right. For the steps and strategies involved, you can take a look at the video tutor solution here. That's from the author of the book. Identify all the forces acting on the object and draw the free body diagram. Draw the vector starting on the black dot. Location and orientation will be graded. The exact length will not be graded. but the relative length to each other will be graded. So you know there has to be a net force back to the right. Okay, so here are the elements that you can actually add. Normal force, weight, drag force, and frictional force on the car. So this one's a little tricky if you think about a car. You think about usually friction stopping you from moving, right? Friction slows you down if you're sliding. But if you don't have any friction between your tires and the road, you won't go anywhere. If your car is just on ice and you try to move forward, you won't go anywhere. It's that static frictional force between your tires and the road that actually propels you forward. So friction here is making you go forward. If not, you would not move. You would just stay where you're at. So the frictional force here is actually to the right. It's keeping the car from sliding back. So I clicked on that one. I'm going to put it here, angle of 0 degrees. Now the drag force, on the other hand, is going to go back the other direction, and it can't be as big as the frictional force, so you wouldn't be accelerating. I'll leave the normal force and the weight for you. Weight's always going to be straight down. Normal force is going to be up, though. So it's a little bit tricky, but think about the tire on ice example about why is the frictional force to the right when you're moving to the right. Same thing if you're trying to walk. Say you're just walking on ice. How do you propel yourself forward? Well, if there were no, if it was just all ice, your feet wouldn't go anywhere. They would just keep sliding back and forth. It's the frictional force that keeps your foot from sliding, and then you're propelled forward. Kind of an interesting problem. All right, let's look at the next one. This one's not complete. Again, put normal force and weight on. Okay, number 8. 3 ice skaters, numbered 1, 2, and 3, stand in a line with each with her hands on the shoulder of the skater in front. Skater 3 is at the rear, pushes forward on skater 2. Assume the ice is frictionless. And we want to draw the free body diagram of skater 2 in the middle. Okay, and here are our choices. Normal force, contact force from skater 1, contact force from skater 2, and the weight. Okay, so let's take a look at this in a little more detail. Okay, so I've just drawn the skaters just as blocks here. It's the same idea. They're in contact with each other. So this is the free body diagram so far of skater 2. Normal force from the ground, weight from the earth. Now 2 is in contact with 3, and 2 is also in contact with 1. So whenever there are contact forces, we have this. This is the force on from skater 1 on skater 2, right? They're in contact with each other. Whenever you're in contact, there's a force perpendicular to the surface. We also have a force from skater 3, right? Because skater 3 is in contact with skater 2. So force from skater 3 on skater 2 would be back this way, right? It's a normal force between them. Maybe it's a little harder to visualize with actual skaters. That's why I did this with boxes. So box 3, box 2, box 1 correspond to skater 3, skater 2, skater 1. Okay, so if the hands of skater 3 are on skater 2, that's where the normal force is, this direction. Here's skater 2, hands are on the back of skater 1, so skater 2's hands are on the back of skater 1, pushing on skater 1, but the back of skater 1 is pushing back onto skater 2. That's why you have the force this way. Okay, so this is sort of like the hands of 3 on 2. This is the back of 1 hitting the hands of 2 going back the other way. Okay, good, so something like this. All right, let's look at the next one. Okay, so the next problem here is actually from Chapter 5. So Chapter 4 and 5 are really related to each other. Chapter 5 is applications of Newton's laws. Okay, so we get to put into practice what we learned in Chapter 4. Some books just have Chapter 4 and Chapter 5. Some other authors combine that into one big chapter. Here it's just 2 different chapters, really related to each other though. Okay, so let's take a look. 3 ropes in the figure are tied to a small, very light ring. So here's the ring, rope 1 and rope 2. A third rope pulls as shown with 100 newtons this way. What are tension 1 and tension 2? The magnitude of the tensions in the 2 ropes. Okay, good. So we'll be doing a little bit of trig with this one. We're balancing forces here, though. This ring isn't going anywhere, so the forces down have to be equal to the forces up. The forces to the right have to be equal to the forces to the left. Okay, let's take a look at this. Okay, so I've redrawn the picture here. Here's 100 newtons, 30 degrees. Here's tension 1, which is back this way, horizontal. Tension 2 is up this way. So this ring is not going anywhere, so all the forces have to be balanced. Why don't I just call this T3 so I don't have to keep writing 100. So we've got T3 in the X, T3 in the Y. So I just have broken T3 into its components. Part in the X direction, part in the Y direction. And again, all the forces are balanced, so I know that T1 has to be equal to T3 in the X. And I also know that T2 has to be equal to T3 in the Y, right? Because nothing's going anywhere. All the horizontal forces have to be balanced. All the vertical forces have to be balanced. Okay, so that's a good start. We also know then that T1 is T3 in the X direction. Now look at this triangle here. This is a 90-degree angle here. So the cosine of 30 degrees, just do this kind of off to the side, the cosine of 30 degrees is T3x over T3. So then T3 times the cosine of 30 will give me T3 in the X. And that's what T1 has to be equal to. So you can take this for T3, plug it in here, and then you have T1. It's the same idea for T3 in the Y. Again, looking at this triangle, the sine of 30 degrees is the opposite side, T3 in the Y, right? Here's 30 degrees, opposite over hypotenuse, over T3. So then T3 times the sine of 30 is T3 in the Y direction. There are certain ones that you remember, right? Like sine of 30 is a half. So this turns out to be 1/2 times 100, so 50 newtons. I happen to know that the cosine of 30 is like 0.866, so you can figure it out that way. Okay, so this is balancing forces and using some trig skills here. Okay, excellent. Let's look at the next one. Okay, so this is a little bit of a sort of biology related maybe. When you bend your knee, the quadricep muscle is stretched. This increases the tension in the quadriceps tendon attached to your kneecap, which in turn increases the tension in the patella tendon that attaches your kneecap to the lower leg bone, the tibia. Here's a picture of this, by the way. Patella, femur, tibia. Here's the patella tendon. Here's the quadriceps tendon. Okay? Simultaneously, the end of your upper leg, which is the femur here, pushes outward on the patella. Right, so this force is up, this force is this way, but there's a force from the femur on the patella. The figure shows how these parts are arranged. What size force does the femur exert on the kneecap if the tendons are oriented as in the figure and the tension in each tendon is 60? So this is 60, this is 60. We're assuming that the patella is not going anywhere. What is the force from the femur on the patella? Okay, so let me draw a nice picture of this and we can take a look at it in more detail. Okay, so here are the forces from the tendon. 60 newtons up this way, 60 newtons back this way. In my problem, it's 42 degrees. I think it's the same for yours. So the force coming this way on the patella have to balance, the force has to balance this force and it has to balance that force. So I switched to green for that, to get that force. So we got to cancel out the 60 newtons that goes this way. Remember, because the patella is not going anywhere. And then we also have to have 60 newtons back this way. And that would cancel out this one. So it literally doesn't cancel them out. They're still there, but this balances the forces. Okay, let's take a look at this in a little bit more detail. Okay, so this 60 newtons up here has a part this direction and a part this direction. And we know that this is 42 degrees, so this is also equal to theta here. So what we'll have to do is figure out the net force in the green that's to the left and the net force that is down, right? Because this is 60 newtons. This is going to be smaller than 60 newtons here. So you're going to have a certain amount left down this way after you get done with all this, and then you're going to have an amount this direction afterwards. So this is the after picture of the green part here. Okay, so let's figure out how much of this 60 newtons is right here. So it looks like the sine of 60, maybe I'll just call this like tension y, and this one could be tension x, just so we know what we're talking about. Okay, so the sine of 60 would be ty over 60 newtons. So then you can figure out, sorry, it's not 60 degrees, it's 42 degrees. 42 degrees, right? Theta. So the sine of 42 degrees is ty over 60 newtons. The cosine of 42 degrees, and this is just going to give you the magnitude of the force, is tx over 60 newtons. Okay, so let's actually get some numbers for this one. Okay, so this ty turns out to be 60 times the sine of 42. Sine 42. I'm in degree mode. This is about 40.15 newtons. This tx here turns out to be 60 newtons times the cosine of 42. 45.69. Sorry, 44.59. Wow, how did I read that so poorly? 44.59 newtons. Okay. So that's just for this force, breaking it into its parts. We've got this one going in the opposite direction. So this is also in the y direction, whatever we want to call this one. Why don't I call it t prime y or something like that? Again, you can call these things whatever you want to. So the net amount of force for the green ones, this one at this angle, this one straight down, the net amount of force to the left is only due to this one. So this is 44.59 newtons, right? That's the only horizontal force from the green ones. It just comes from the horizontal component of this one. Vertically speaking, this 60 newtons has a part here and a part here. They're in opposite directions, so I'll have to do 60, that's what's down, minus the one that's up, 40.15. 19.85. That's how much this one is. Okay, and then the net amount would be 19.85 squared plus 44.59 squared. These are all in newtons. We'll have to take the square root of that. That should give us the answer for this one. Okay, so I'll leave that part to you. Okay, here's the next one. An early submersible craft for deep-sea exploration was raised and lowered by a cable from a ship. When the craft was stationary, the tension was 7,500 newtons. Okay, so when it's not moving, it's just balancing the weight. When the craft was lowered or raised at a steady rate, the motion through the water added 1,800 newton drag force. Okay, what was the tension in the cable when the craft was being lowered to the seafloor? What's the tension when it was being raised from the seafloor? Okay, interesting problem. Let's take a look at maybe the first part. I'll leave the second part for you. Okay, so when it's stationary, they're telling you the tension is 7,500 newtons, so that must be what the weight is equal to. Okay, now that's just when it's stationary. Now for part A, it's being lowered to the seafloor at a constant speed. So let's look at all these different forces as it's being lowered. So if it's moving this way, if the velocity is this way, the drag force must be the other direction. So you know you've got a drag force this way. The weight is still this direction. And you've also got tension this way. Right? So maybe I'll call this T lowering. Because the tension's not going to be the same now because you're being helped out by this drag force. So when you're just holding it steady, there is no drag force. The tension and the weight are equal to each other. When you start to lower it, The drag force is the opposite direction that it's moving, so it kind of helps you out. The tension's not going to be as great here. The weight's the same, 7,500 newtons. The drag force is whatever they told you it was in the problem. I can't remember, 1,800 or something like that. So all the upward forces have to balance the downward forces. You could solve for the tension while you're lowering it. It's kind of interesting when you raise it, the drag force is going to be in the opposite direction. So, you know, the tension here, the tension when you're raising it are going to be in the same direction but a different magnitude. So when you're lowering it, the drag force is helping you out. When you're raising it, you have to combat the drag force. And again, up is equal to down. The total up is equal to the total down in terms of forces because it's going at a constant speed. Constant speed means acceleration of 0. Okay, interesting problem. Free body diagrams definitely help with these problems. Okay, let's look at the next one. Okay, so let's take a look at this one. The forces in the figure are acting on a 3 kilogram object, so we know the mass. How much is the acceleration in the x direction? Okay, so you'll have to figure out the net force in the x direction. So in the y direction, if you look at this force is at some kind of angle. Actually, this is 3, 4, this force must be 5, but we are concerned about how much of the force is in the x direction, how much is in the y direction. When you see Newton's second law, F is equal to ma, you see the little vector sign over F and the little vector sign over a. That means it's a reminder to you. It means to make sure that you look at the x direction independent from the y direction. Okay, so in terms of, let's just say the y acceleration, there is none because there's no net force in the y direction. This vector at an angle here has 3 newtons up. Here we've got 3 newtons down. There is no net force in the y direction. They're not even asking for it, but it would be 0 in the y direction. Now in the x direction, this vector has 4 newtons to the right, 2 newtons to the left. The net force is 2 newtons. Here's the mass. You could figure out the acceleration from Newton's second law. Okay, so I'll leave that one for you. Next problem. How much force does a 61 kilogram astronaut exert in his chair while just sitting at rest? Okay, and then how much force does the astronaut exert on the chair while accelerating straight up at 11 meters per second squared? Okay, interesting problem. Let's take a look at it. Free body diagrams are really going to help with this problem. Okay, so the mass of the astronaut is 61 kilograms. Just sitting in the chair at rest, all the forces are balanced. Normal force from the chair on the astronaut is up. The weight of the astronaut is down from the Earth. And we know that this is equal to m times g. So the weight would be 61 kilograms. Sorry for that noise. It was an announcement to get a free vaccination immediately. I've already done that, so I don't have to worry about it. 61 kilograms times 9.8 meters per second squared. This will tell you the weight then. So we've got 61 times 9.8. 61 times 9.8. This is the weight, 597.8 newtons. That's not going to change. That's the force due to the Earth pulling on the astronaut. Now, sitting at rest, these are the only two forces. They're equal to each other. So this has to be 597.8 newtons. This is the normal force from the chair on the astronaut. That's the same thing as the normal force from the astronaut on the chair. That's what they're actually asking for in the second part, but they're equal to each other. The normal force from the astronaut on the chair is equal to the normal force from the chair on the astronaut. Now that force is different in this part, right? If you're accelerating upward, this normal force, I'm even going to exaggerate it a little bit. Now if you're accelerating up, this normal force has to be bigger than the weight. Then you actually have a net force and you have an acceleration this way. Okay, the weight's the same, 597.8 newtons, but the normal force has to be bigger now. So the normal force from the chair on the astronaut has to be bigger. This is what actually, if you just think about the astronaut, this is what gets the astronaut accelerating up. It's the chair. Of course, the chair is connected to ship, and the ship is connected to the engine, so ultimately it's the engine that propels everything upward. But if you just look at the forces on the astronaut, it's the seat that's accelerating the astronaut up. Okay, so we've got our free body diagram. Here's the acceleration. The mass is also given. We can figure out this normal force. So Newton's second law seems so the way it's written, right? F is equal to ma. Seems not that bad, only 3 variables. It's this part that's tricky, the actual forces. I put a little box around them. What are the actual forces? Normal force up minus the weight that's down. That part's not bad. That's Newton's second law. We use that to solve these force problems. It's filling in this part that becomes tricky, the actual forces. So Newton's law you could use almost for everything. So even though it looks F is equal to ma, not so bad so far, it's when you start getting into these problems where you actually put real life forces on that it becomes a little bit trickier. But what we're looking for is the normal force. We'll have to do a little bit of algebra, add the weight to both sides. So ma plus the weight gives you the normal force. Okay, so the mass, 61 kilograms. The acceleration, 11 meters per second squared. Plus the weight, where you've got to overcome the weight. That's how much the normal force is. So it's much, much bigger, right, than we had before. This is an N. Okay, so there is a net force up here. It's just looking at the astronaut, it's the chair that's accelerating the astronaut up. All right, let's look at the next one. Okay, the final problem, actually. A 26 kilogram child slides straight down an incline at 38 degrees. The child is acted on by his weight, the normal force, and kinetic friction. We've got to choose the correct free body diagram. Okay, so the normal force, just a couple of things about this. The normal force is always perpendicular to the surface. The weight is always going to be straight down, and friction is always going to be opposite of the way that we're moving. So the problem with this first one is friction is not this direction. Kinetic friction is the friction of sliding, and it's got to be the opposite direction. Okay, all right, so friction is the correct direction here, but this is not the normal force, right? This should be the weight. So it can't be that one. Okay, so the normal force looks good here, perpendicular to the incline. Here's friction back the other way. But the weight has to be straight down. It can't be that one. Okay, this one's looking good. Normal force this direction, kinetic friction, weight. So it looks like the last one's going to work out here. All those forces are in the correct direction. Part B, how large is the normal force of the slide on the child? Okay, so let me draw a little picture of this one. Okay, so here's the picture I have. I just represented the child as a block here. Then here's the normal force like you saw. Friction's going back the other direction. Weight is straight down. So remember what we did with motion on a ramp in the last chapter. You can break the weight into its components, and we're looking at it like this again. X and Y. So this weight has part down the incline. This one turns out to be W sine theta. And it has a component that's perpendicular to the incline. This is the weight times the cosine of theta. Okay, so this child's not flying off the incline up or down like this or melting through the incline. So the normal force this way has to be equal to the component of the weight back this way. So the normal force is equal to the weight times the cosine of theta. So the normal force would be mg cosine theta. Okay, they're asking for the normal force. You can solve for the normal force. While we're at it, let's look at motion down the incline this way. They don't ask about it, but I'm going to tell you about it anyway. So I'm looking at the acceleration down the incline. So F is equal to ma. Why don't I call it x direction, because I called this x direction. And then the actual forces down the incline, you've got mg sine of theta, or the weight sine of theta, that's down the incline, minus kinetic friction back the other way. Okay, again, they don't ask about this. I'm just showing you what would happen down the incline. So if you're accelerating down the incline, you've got to look at the actual forces, down the incline or opposite direction of the incline. Weight sine theta is actually what pulls you down the incline, and if you happen to have friction back the other way, you have to include that. Okay, that's homework 3. If you have any questions, just email me, and I will talk to you soon. Bye-bye.